So in this session we'll be now studying about the separately excited DC motor. So in case of separately excited DC motor, as the name itself suggests, the excitation is separate from the main armature circuitry. If we look at the equivalent circuit diagram of a separately excited DC motor, you will have an armature resistance here, so you have a separate armature circuitry, so you'll be supplying a voltage Vt to the armature circuitry. A current IA will flow through this circuit, the resistance of this armature being Ra, the induced voltage across the armature being Ea, fine. And the field circuitry will be separate, and current IF will be flowing through the circuit. So this is your separately excited DC motor. The main thing here is that your field circuit and the armature circuit are separated from each other. Now if you have a look at the voltage, the KVL equation, you still have the same equations as were valid in case of a shunt DC motor. Vt is equal to Ea plus IaRa, or Ia is equal to Vt minus Ea divided by Ra. So if you were to find out the speed equation of a separately excited DC motor, it will come similar to that of the shunt motor. So once you substitute Vt is equal to k5 omega in the above equation and then obtain the value of omega, you will be getting Vt divided by k5 minus Ra into induced torque divided by k5 square. So you have the same speed equation as that in case of a shunt DC motor. So you will actually be having the same torque speed characteristics. So if this is omega, this is your torque. So you'll see that the profile of the speed torque characteristics of a separately excited DC motor and that of a shunt DC motor will be similar. You'll obtain a graph like this. So this will be the effect. This will be without armature reaction, and definitely with armature reaction, as we have seen the case, there will be this reaction will be something like this. So this will be with armature reaction and this will be without armature reaction. So we have seen that with armature reaction the flux will be weakened, and flux weakening causes increase in the speed of the DC motor. So this is your torque speed characteristics of a separately excited DC motor, same as that of the shunt DC motor. So same speed control strategies can be used for a separately excited DC motor. So if we talk about separately excited DC motor, you'll have the same strategies, the field control method by changing RF, there will be the similar effect. You increase the value of RF, IF decreases. IF decrease means the flux decreases, that decreases the induced voltage, that increases the armature current, that increases the induced torque, that will cause the speed of the motor to increase. And then there will be the armature control strategy, in which case you will, by changing the terminal voltage that's applied to the armature circuitry. So if we increase the terminal voltage to, that's being supplied to the armature of the DC motor, the speed will increase. If you decrease that voltage, the speed will decrease. So more or less, the separately excited DC motor and DC shunt motor, their terminal characteristics, that's the torque speed characteristics, they are similar. Their speed control strategies will be almost similar in all the cases, with a slight difference. But there is not much difference between separately excited DC motor and shunt DC motor in terms of operation. Physically, the systems, in case of a shunt DC motor, the field winding and the armature winding, they are electrically connected and they are in parallel to each other, while as in case of a separately excited DC motor, the field winding and the armature winding, they are electrically isolated from each other. There is no physical connection between the armature and the field winding. The connection will only be purely magnetic between the field and the armature circuitry. Now we'll be doing some numericals on this. So these numericals will be valid for both shunt as well as separately excited DC motor. So this is your question at 25. A 25 kilowatt, 125 volt. Separately excited DC motor has been given to us and is operated at a constant speed of 3000 rpms. A separately excited DC motor 25 kilowatt 125 volt is operated at a constant speed of 3000 rpm with a constant field current. Such that open circuit armature voltage is 125 V. The armature resistance is 0.02 ohms. Ra is equal to 0.02 ohms, and therefore compute the armature current. We have to calculate the armature current, the terminal power and the electromagnetic power. Terminal power, that's the power that's being supplied. The electromagnetic power, that's the power that will be generated or induced in this machine. And torque, when the terminal voltage, electromagnetic power and torque. So electromagnetic torque will again refer to the induced torque of the machine. When the terminal voltage is we have been given two conditions of the terminal voltage. One is 128 volts and second one is 124 volts. Fine. So if you see the solution of this is a separately excited DC motor. Now we have been given in the first case, in case number A, terminal voltage is how much? 128 volts, and the open circuit armature voltage is 125 volts. That means EA is equal to 125 volts. Therefore what is RA? RA is 0.02 ohms. We know for a separately excited DC motor the armature current is given by VT minus EA divided by RA. So substituting these values, 128 minus 125 divided by 0.02, that comes out to be equal to 3 divided by 0.02 is equal to 150 amperes. Fine. So we have been given our 125 kilovolts, 125 volts, separately excited DC machine. So 150 amperes is coming out to be, since the terminal voltage is greater than the induced voltage EA, so this is actually a motor being represented in this case here. So IA will come out to be 150 amperes. So this will be, power will be flowing into the motor. So what will be the input power to this motor? This will be, we have calculated the armature current. What will be the armature current has been done. Now let's do the terminal power. So terminal power of this machine will be, that is the power that is being supplied, will be equal to VT into IA. VT is equal to 128 and IA we have just seen 120 amperes, 150. So this is 128 into 150, that comes out to be equal to 19.20 kilowatt. Right. So this is the power that's going into the motor. And what will be the electromagnetic power in the motor? Electromagnetic power, that will be the induced power in the motor. That will be given to us by EA into IA. That will be 125 into 150, and that's equal to 18.75 kilowatts. Fine. So this is your terminal power, your electromagnetic power. And now the electromagnetic torque, or the torque equation of this motor, you can get it directly from the electromagnetic power that was derived, EAIA divided by omega. So this is the same formula that we have been using for torque. Torque is equal to power divided by omega. EAIA, EA is equal to 18.75 into 1000, and as far as omega goes, the speed of the motor has been given to us. It is 3000 RPMs. 3000 RPMs into RPM does not represent the SI unit of the motor, so 3000 into 2 pi divided by 60. So if we calculate this, this will come out to be equal to 59.7 Newton meter. So this is case A, where the terminal voltage that is being applied to this motor is 128 volts, whereas the internal generator voltage was 125 volts. So similarly you can do case B. Vt is equal to 124 volts now. Fine. So once you calculate Vt with 124 volts, you will see that since current will come out to be negative, you will put Vt is equal to 124 minus Ea is 125, armature current is 0.02 is. So this comes out to be equal to 50 minus 50. So that means now the current is no longer flowing into the motor, it is flowing, it's into the machine, it's flowing out of the machine. That means Ia is flowing out, and therefore the machine acts as a generator. So rest of the equations will be same. You have derived Ia. So once you have the Ia, you can find out the terminal power given by Vt into Ia, the electromagnetic power Ea into Ia, and the electromagnetic torque P omega divided by the same speed, that is 3000 rpms. So this is this is one. Let's do another problem. For the same problem, continuing with the same problem, for the same problem as above, it has been seen what is being recorded, that Vt is equal to 123 volts, and what else is given to us? Terminal power is given to us equal to 21.9 kilowatts. For the same problem with Vt equal to 123 volts, terminal power equal to 21.9 kilowatts, and acting as a motor, that's given to us in the question itself, and acting as a motor. Calculate the speed of this. Calculate the speed of the motor. Fine. So for the same problem with Vt equal to 123 volts, the terminal power equal to 21.9 kilowatts, and the motor acting as, we have to calculate the speed of the motor. So we know terminal power is equal to Vt into Ia. So if this is 21.9 kilowatts and Vt is 123, we get Ia equal to 21.9 divided by 123, (178 amperes). So the armature current in this circuit is 178 amperes. Therefore, what will be the generated voltage? Therefore, Ea will be equal to, we know Vt is equal to Ia plus IaRa plus Ea. So Ea will be equal to Vt minus IaRa. Vt is 123 minus Ia is 178, and Ra for this machine was 0.02 ohms. So this comes out to be equal to 119.4 volts. Fine. Now we know EA is proportional to speed. At a speed of 3000 rpms, the internal generator voltage was 125 volts. At a speed of whatever is the speed right now, the internal generator voltage is 119.4 volts. So you can say, since E is proportional to omega, you can say 125 volts is equal to K times flux K, phi and omega, where rather K dash, phi and N. Fine, because we have been given the speed has been given in rpms, K dash 5 N. This will be case 1 N1 rather, and 119.4 volts will be equal to K dash phi N2. This will be equation number 2. So dividing 1 and 2, where K dash and phi they remain constant, we will be getting 125 divided by 119.4 is equal to N1 divided by N2. N1 is the speed at 125 volts, N2 is the speed corresponding to 119.4 volts. We know N1 is equal to what? 3000 rpms. So we can write here at 3000. Therefore, what will N2 be equal to? 3000 into 119.4 divided by 125. So this comes out to be equal to 2866 rpm. So this is in rpms. Fine. So this will be your voltage, this will be your speed corresponding to a terminal voltage of 123 volts when this is acting as a motor. So in another question, what we have been given is this is your circuit diagram. You have a shunt DC motor, VT, the terminal voltage is equal to 250 volts. So this is a 100 HP, 250 volt, 1200 RPM. So these are the ratings of this machine. Shunt DC motor. The armature resistance is 0.03 ohms. R is given to us 0.03 ohms. And what else is given to us? And a field resistance of 41.67 ohms. So 100 HP, 250 volt, 1200 volt RPM shunt DC motor with armature resistance of 0.03 ohms and a field resistance of 41.6 ohms. We are ignoring the armature reaction here. We are ignoring the losses. The motor is assumed to be driving a load with a line current of 126 amperes. Line current here refers to this current, 126 amperes. Fine. At an initial speed of 1103 rpms. So IL is equal to 126 rpm at 1103 rpms. This is not the line current at 1200 rpm, this is the line current at 1103 rpms. So we need to find out what is the motor speed if the field resistance is raised to 50 ohms. We have to calculate what is motor speed if RF is equal to 50 ohms, if RF is raised to 50 ohms. So at 1103 rpms at 126 amperes, armature current, this is armature current, this is field current, fine. So IA1 will be equal to IL1 minus IF1, fine. So what is IL1? IL1 is equal to initial line current that's being given to us 126 amperes minus IF1. What will be the field current? Field current will be equal to VT divided by RF. VT is equal to 250 divided by RF is 41.67 ohms. So this comes out to be equal to 120 amperes. Corresponding to this EA1 will be equal to VT minus IA1 into RA, where VT is equal to 250 minus 120 into RA is 0.03 ohms. So that will be equal to 246.4 volts. Now what will be the field current? What will be IF2 now? IF2 will be equal to VT divided by RF2. So RF2 basically means here VT is still going to be the same, 250. RF2 means here the field resistance has now been raised to 50 ohms. So therefore, with this in mind, our IF will be equal to 5 amperes. So with IF2 equal to 5 amperes now, there's one more thing in the question. What is the motor speed if RF is equal to 50 ohms and armature current is constant? So we are not actually bothered about IA2. IA2 is constant, it will be equal to IA1. We have to derive now the speed at this field current. Initially the field current was IF1, that was 250 divided by 41.67. So that IF was more. Now IF has become equal to 250 divided by 50. So IF has actually decreased. Flux decreases. We know that with decrease in flux, the speed will increase. Here the equation will be now. We know EA1 is equal to K dash phi 1 N1, where N1 is the initial rotor speed, and EA2 will be equal to K dash phi 2 N2, fine. So phi 1 is corresponding to a field current of 250 divided by 41.67 ohms. Phi 2 is the flux corresponding to a field current of 250 divided by 50 ohms. Now therefore, dividing these two equations, we'll be getting EA1 divided by EA2 equal to K dash and K dash goes phi 1 N1 divided by phi 2 N2. So this is basically different from the previous problem. In the previous problem flux was constant, so flux we were cancelling out, but here flux is also changing as well as the speed of the motor is changing. So this is what we need to find out. Now since the armature current has been given to us, we have been told that the armature current is constant. If the armature current is constant, EA, that is equal to VT minus IA RA, will still remain the same. That means EA1 and EA2 will basically now be equal for same armature current. EA1 and EA2 will be same because EA is what? EA is equal to VT minus IARA. So if VT is also not changing, RA is not also changing, IA is also not changing, so EA1 and EA2 will be same. So therefore this equation now becomes phi 1 N1 divided by phi 2 N2 is equal to 1. Fine. Therefore N2, that is the speed that we want to actually find out, is equal to phi 1 divided by phi 2 into N1. Now to find out phi 1 by phi 2, we do not actually know what is phi 1 by phi 2, we know IF1 and IF2. We have been given a magnetization curve along with this question. We know the magnetization curve is something like this. Fine. This is your field current. This is your field current IF, and this is your voltage terminal. This is your voltage generated voltage EA. Fine. So this curve is something like this. Here the value is $50, $100, $150, $200, $233. Fine. And this is 1 ampere, 2 amperes, so on. Now what we are actually concerned with, we have two values of field current. The first value of field current is the second value of field current is IF2 is equal to 250 divided by 50 volts. The first value of field current was 250 divided by 41. The initial resistance, the field winding resistance was 41.67 ohms. So 250 divided by 41.67 ohms. That's equal to 6 amperes. Fine. So this magnetization curve is given to us. So at 5 amperes, I'm going to directly write now this at 5 amperes what is the voltage, and at 6 amperes what is the voltage. So at 5 amperes, from the graph that has been given to us, the voltage is 250 volts, and at 6 amperes the voltage is 268 volts. Fine. So 6 amperes is corresponding to IF1 and this is IF2. Therefore this will give us phi 2 and this will give us phi1. So in nutshell we can say phi2 divided by phi1. Since these two graphs are proportional to each other in the linear region, phi2 divided by phi1 will be equal to 250 divided by 268. Fine. So now we actually need to find out n2 equal to phi1 by phi2 into n1. Phi2 by phi1 is 250 divided by 268. So phi1 by phi2 will be 268 divided by 250. So therefore n2 is 268 divided by 250 into n1. What was the initial value of the field current corresponding to that? We were having 1103 rpms. Fine. So 268 into 250, this comes out to be equal to 1187 rpms. So this is our, so let me just repeat what we have done here. So we have been given a motor whose armature resistance is 0.03 ampere ohms. Field resistance initially was 41.6 mn ohms. The initial line current was 126 amperes for a speed of 1103 rpms. Terminal voltage is given to us as 250 volts. So now what is happening? We are increasing the field resistance from 41.67 ohms to, we are increasing the field resistance, so naturally we are expecting the speed to increase 41.67 ohms to 50 ohms, and we want to see what will be the new speed of this motor, assuming the armature current is constant. So we first of all find out what will be the new armature current, and what will be the armature current, what will be the new field current at a RF2 of 50 ohms. And we have this equation, since we know that EA is equal to K dash phi1 into N1. So EA1 is equal to phi1 N1, EA2 is equal to phi2 N2. Dividing their two equations, we will be arriving at this equation. Now the main thing here to note was that since the armature current was constant, EA, which is equal to VT minus IARA, EA1 and EA2 will be same. So therefore phi1 N1 divided by phi2 N2 was equal to 1. Therefore N2 is equal to phi1 divided by phi2 into N1. Now to find out phi1 by phi2, we are actually referring to the magnetization curve. This magnetization curve you can actually find from any book. So this is a typical magnetization curve for 250 volt DC motor running at a speed of 1200 rpms. So from this, directly looking at the curve, at a corresponding to a field current of 5 amperes, the generated voltage is 250 volts. Corresponding to a field current of 6 amperes, the generated voltage is 268 volts. Since we know that generated voltage is proportional to the flux, so we can directly write that phi2 divided by phi1 will also be equal to 250 divided by 268. Fine. 250 divided by 268 here is actually the generated voltage that we can actually look from the corresponding magnetization curve. So once we have the phi2 by phi1 value, we can then find out n2 by substituting the initial speed value. So this is all for today for this session.